Hi, good morning everyone. Today I'm more than glad to present our work, CROMOSim, a deep learning-based cross-modality inertial measurement simulator. It is authored by Yujiao Hao, Dr. Boyu Wang, and Dr. Rong Zheng. First, I'd like to show the motivation of our work. The scarcity of well-labeled and nature-like MU motion data is due to multiple reasons, such as the collection of some activities are physically demanding for certain population groups, the fragile ones like the elder people or young children. Also, although the MU sensors are said to be a non-intrusive way for mobility assessment, they will impact people's movement when being installed at multiple on-body locations. Nevertheless, the acquisition of ground truth for the human activity labels or human pose parameters is a tedious and labor-intensive procedure involving expensive equipment, and most time they are limited in indoor environments. All the factors together hinder the collection of a large-scale MU dataset for human motions. Therefore, a natural way of tackling the data scarcity in MU is to translate it from other relatively more abundant input modalities. In this work, we propose a sensor simulator that generates real MU-like readings from arbitrary on-body locations, instead of being featured for a specific downstream application. And here is its pipeline overview. We consider two data modalities as input here: the pervasively available but inaccurate molecular video data, and the relatively small but highly accurate one, the motion capture system data. We extract the body shape, angle of each body joint, and the global motion trajectory from either input source, and represent the global motion sequence by an SMPL model. Sample 3D motion trajectory from the selected on-body position, give it as input to our simulator network, and then predict the MU readings under a global coordinates frame. It requires one more step to transform the MU readings to a sensor frame, which is how a real sensor works. And in the following slides, I will give a more detailed insight into the key components of this simulator pipeline. Well, the SMPL, which is short for the Skinned Multi-Person Linear Model, is a full-body mesh-style representation of the human body. Besides the poses, it can represent the human body shape at the same time. It has many extended versions with hand, face, or muscle dynamic features, and we take the basic version that represents the human body with 23 joints. We made a simple experiment to compare it against another widely used representation, the skeleton model, in an MU simulation context. We analytically compute 3-axis accelerations from both models and compare the results against a real accelerometer attached to the subject's lower back. The motion sequence was extracted from the MoCap data. In this figure, shows the calculation from the pelvis joint positions of a skeleton model, and in the right ones, shows taking the sequence from SMPL lower back skin mesh. We can see that the right one fits better to the ground truth sensor reading than this left one, especially in the range from 100 to 300, right? And it is mainly attributed to the fact that the sensor is attached to the skin surface rather than directly on human bones. When taking MoCap as input, life will be much easier because the input data already has a high quality. It is not only very accurate with an average position error smaller than 1 millimeter, but also has all required ingredients, include the 3D global motion trajectory of the subject and her body shape. We may fit an SMPL model to MoCap data with MoSH++ and take the selected on-body position trajectory as input to generate MU data. This procedure may introduce further noise to the data and enlarge the position error to be larger than 6 mm, but it is still far more reliable than video data. And the example here shows when the human subject moves her hand. A blue curve was extracted from the SMPL on-body mesh around the wrist, and the gray curve was the Vicon ground truth collected at her palm. When taking video sequence as input, the idea is similar, but the procedure is much more complicated. Human pose estimation with single camera video or even handheld camera is an active research topic in the computer vision field. It is challenging yet interesting. The example we show here is a running video clip from the real-world dataset. A subject is running in the wild, captured by a handheld camera. We take wipe to predict the human body shape and pose, but unfortunately, it is only capable of estimating an in-place movement where the global orientation and position are missing. Thus, we try to complement that with robust 3D, which is capable of dealing with moving cameras and predicts the depth map of each frame. After combining the estimated 3D global trajectory with the in-place body pose and shape, we get the essential inputs for sensor simulator now. Well, with extracted 3D positions and orientation, one may analytically compute the acceleration and the angular velocity. However, it will fit the ground truth MU readings only in an ideal world, where both the input global motion trajectory and the collected real MU readings are 100% accurate. But we all know it won't happen in the real world. Both the input and output are noisy. So we propose to learn the mapping or the relationship between the two with a neural network instead of directly do the computation. It is unrealistic to conduct supervised learning at all over the body positions. We only select 3 on-body locations with different range of motion for model training. Right wrist, right foot, and pelvis are selected. We train one model per input-output pair. For example, MoCap as input, gyroscope as output, video as input, and accelerometer as output. Therefore, 4 models were trained in total to serve 2 different input data modalities and output sensor types. While in the data fidelity evaluation, we compare CROMOSim against MuSim and analytically computed MU readings, which is called MuCall. MuSim is an open-source simulator released a decade ago. To save space, we only show the gyroscope simulation here. The plots were generated with an unseen subject at unseen body location, which is the subject 5 of total capture with the left wrist. The left column shows the simulation from MoCap data, and the right column shows the one from video data. MuSim works poorly in both cases, and the analytically computed one failed in the video extracted data. But CROMOSim generated sensor readings that are close to the real ones in both cases. And Table 1 shows the qualitatively evaluation for all data trials. The result is following the plots, indicating the CROMOSim can generalize to unseen subjects and unseen sensor locations. And to evaluate the performance of CROMOSim, we conducted human activity recognition evaluation according to the MoTube protocol as the downstream task. The MU data were first simulated with molecular video data from the real-world dataset, then distribution mapped to the target dataset. Taking the simulated data and the real ones for public datasets, we carry out real-to-real, virtual-to-real, and mixed-to-real evaluations on the random single-subject holdout experiments on 2 different datasets. We tested real-world and PAMP2 datasets here. They differed in the subjects, sensor placement, and activity set. PAMP2 replaced standing with cycling, jumping with rope jumping when compared to real-world. Both experiments demonstrate that the CROMOSim is helpful in HAR as the model performance is enhanced in the mixed-to-real case in both datasets. Well, in conclusion, CROMOSim is aiming at simulating high-fidelity MU sensor data, and the simulation can take either MoCap or video as the input data source. It allows arbitrary on-body location simulation, and now we are wrapping it up with better implementation, and hopefully can release it very soon. Thank you for listening.